Okay, everyone, good morning. Let's get started. Any issues with lab 1? I think that was due last week. Did everyone get that done okay? Great. Did you get all your questions answered in lab? Any issues? Good. Okay, so we have a new quiz for this week that I posted yesterday. Make sure you take quiz 2 by Friday. And I checked the scores for quiz 1 and 2. They look fine. I thought I'd just run through them real quick, though, in case anyone had any questions. Sorry, wrong one. Quiz, there we go. Okay, so the first quiz covered programmed I/O. There's a question on here about the size of a peripheral's I/O space, or what is the size of a peripheral's I/O space whose address begins at 1100 in hex and ends at 2 CEF. So you just subtract and add 1 and convert to base 10, 7,152 bytes, right? Suppose variable B contains the value 1, 2, 3, 4 in hex. To what value will it change after executing the code? B equals B or, and 1 shifted 5 bits to the left. So that is going to set bit 5 in B, if it's not already set. And bit 5 is in the second hex digit from the right, and it has a significance of 2 in that digit, right? So if you look at that value, the second hex digit from the right is 3, and bit 2 is already set in 3, right? Because 3 is 0011, right? So it won't, I don't believe it changes that, right? Yeah, it doesn't change it, right? Suppose variable B contains the value 1, 2, 3, 4. To what value will it change after executing the code? B equals B and 1 shifted by 5 bits to the left minus 1. So that's going to 1 shifted to the left by 5 bits, and then subtracting 1 will turn on 5 bits, right? That should be 1, 1, 1, 1, 1. And then we take those 5 bits and shift it left 1 bit. So you still have 5 bits turned on, but now they've been shifted 1 position to the left. So that's going to correspond to bit positions. It was 4 down to 0 before we shifted it, right? So if you just had this sub-expression, that would be 1 shifted 5 bits to the left. That would turn on bit position 5. If you subtract 1, it'll turn on bit position 4, 3, 2, 1, and 0, right? So that'll turn on bits 4 down to 0. And then if you shift that 1 bit to the left, that'll shift those two the 2 bit positions that comprise the range. So instead of 4 down to 0, it'll become 5 down to 1, right? And then if you do a bitwise AND, that's going to mask out bits 5 down to 1. Does that make sense? Now bits 5 down to 1 is going to span 2 hex digits, right? So 5 down to 1 will cover 4 bits out of the rightmost digit and 1 bit, 2 bits out of the second to leftmost digit, right? Make sense? Okay, so this is what I just said. So this will give us 5 1 bits. So after you shift these 5 1 bits, 3 of those bits will correspond to the upper 3 bits of the rightmost hex digit, right? And then those 2 will be the lower 2 bits of the second hex digit. Okay, so yeah, and then, so what'll end up happening is that the 1 and 2 go away, right? Because those hex digits aren't covered by any of the 1 bits. The 4 will stay 4, because that 4 is 0, 1, 0, 0, and that's covered by, yeah, that part, right? And then the 3 will also stay 3 because you still have the 1, 1 corresponding to 3. So I think you're going to just get 0034, right? Yeah, 0034. Does that make sense? Okay, suppose you want to set bit 3 and variable b to 0. What line of code will accomplish this? So we have 4 options here. Usually the way you do that is through, if you want to set a bit to 0, use an AND, right? Not an OR. So that rules out these two guys, these two options with OR, right? This is the one that I propose to use in class. So you take 1 shifted by 3 bits to the left, complement it, and then do an AND, right? So basically this will turn off all but bit 3. This one will mask off bit 0 and then shift the whole thing 3 bits to the left. That makes no sense at all, right? So it must be D. Suppose there's a 32-bit variable named IOStat containing a bit field 4 down to 2 that you want to read. What expression will accomplish this? So IOStat, 1 shifted by 5 bits minus 4 will turn on basically just 5 bits, right? 5 1 bits, and then we shift that. We complement that, and so this is going to mask off all but the lower 5 bits of IOStat. You guys with me? Right. So now we got the lower 5 bits of IOStat, but then we shift the whole thing 2 bits to the right. Okay, so that'll give us the original IOStat, but instead of bits 4 down to 0, it'll be 4 minus 2 down to 0, right? Make sense? You guys with me? Okay. All right. Now there's another option here. This one is a different approach where if you want bits 4 down to 2, you can shift the whole thing 27 bits to the left. And why is it 27? It's 27 would be 32 minus 4, right? Minus 1, I guess, right? Yeah, 31 minus 4, rather, sorry. 31 minus 4. Because what that'll do is that'll take bit 4 and move it all the way up into bit position 31, right? Because we're taking 4 and we're shifting it 27 bits. So you're adding 27 to 4, right? So you're taking bit position 4, adding 27, that makes it bit 31. And so the original bit 2 then would also be in bit 29, which is 27 plus 2. And then you can then shift it back to the right by 29 bits, which is going to take bit 29, move it back to bit position 2. So what that's doing is that when you shifted it left, you shifted zeros in the left-hand side, right? And then when you shifted it right, you shifted zeros in the left-hand side, and the only thing that's left over is the original bits 4 down to 2. So that works too. And then this one, IOStat, you shift by, this one shifts everything down by 2, and then just masks off the new low order 3 bits, which would have been, so it takes 4 down to 2 gets shifted down to the right hand side. So the original 4 down to 2 become 2 down to 0, right? And then you just mask off bits 2 down to 0 with 1 1 1. So all 3 of those approaches work. Oh, actually there's another one. In this case, we shift IOStat down to the right by 2, and then we just mask off 4 bits. This is basically the same thing we had before, right? The only difference is how we, yeah. So in this case we had 7. I just used a hard-coded 7, which is 1 1 1, right? In this case, it's the same thing, except I compute 7 by, 1 shifted by 3 is 8 and minus 1 is 7, right? So it's just 2 different ways to get the mask value. Okay, which of the following bit sequences show a pulse width modulated signal with duty cycle 2 in period 5? Period 5, the period is the repeating pattern, right? And the duty cycle is the number of 1 bits. So this one actually matches that, right? Because the repeating pattern is 11000, 11000. So this has a period of 5 and a duty cycle of 2 because of the 2 1 bits. This one has a duty cycle of 1, 2, 3, 4, 5, 6, 7 with a duty cycle of 5, right? Make sense? Okay. Assume a peripheral can raise interrupt every 20 milliseconds. What's the maximum possible interrupt rate for a CPU configured with an edge-triggered interrupt? In this case, an edge-triggered interrupt assume a peripheral can raise interrupt every 20 minutes. So if you can raise interrupt every 20 milliseconds, the raise interrupt line every 20 seconds, is that the idea? Yeah, so if you can raise the interrupt, I think that's the interpretation. There's raise and interrupt. It makes it go from active low to active high, right? So that would give you an edge, right? So is that, I think you just take the reciprocal of that, 1 divided by 0.02. That wasn't worded super well, but yeah, it's just take the reciprocal of 0.02. It's 50 interrupts per second. Okay, that's quiz 1, and I think quiz 2 was shorter. Let's see here. All right, let's skip over that. What percentage of an SPI channel's master to slave bandwidth can be utilized in performing a series of single write transactions? Master to slave? So it's 50%, right? Because 50% of your of the master to slave, right, is going to be address, right? And the other 50% is going to be data, right? Oh, well, it's actually 100% because we're calculating that as the address and the data is accounts. Okay, sorry. In a daisy chain SPI connection between a master and end slaves, how many clock cycles are required to complete a full exchange? So in this case, if you have 1 slave and you do an exchange, it would be 8 cycles, right? But if you're doing daisy chain, you have to be able to shift 8 bits through the first slave and then through the second slave and then back to the master, right? Does that make sense? So it would be n times 8, right? Yeah, or 8 times n. Okay, what is CPUL and CFA? Well, I can tell that CPUL's got to be 1 because clock starts out high, and CFA, if I look at the clock, I can't read the data on the first edge because it's in a state of change. So I got to read the clock on the second edge, right? So CFA must be 1 too, right? So 1, 1, right? What data is written in the transaction below? So written, so MISO is pretty much flatlined, so I don't have any data coming back from the slave. So the data I'm writing is going from master to slave. The first transaction is the address and the flags. The second transaction is the data I'm writing. The trick here is I got to count these cycles. So how am I going to read these? Well, it looks like CFA is 1, right? And so I can read the data on the dotted lines, right? So if I back up and I start from the back, if I count 8 dotted lines from the back, right? 1, 2, 3, 4, 5, 6, 7, 8. I can start with this bit, right? And I can just read the value where the dotted line intersects MOSI, right? So it'd be 1, 1, 1, 0, right? Which is an E and hex, right? And 0, 1, 0, 1, which is a 5. So E5 in hex. Yeah, E5. 1110, 0101. Okay, a bus protocol has 3 wires named D in, D out, and clock. Is this a synchronous or asynchronous? Probably synchronous because there's a clock. What bit's missing from the timing diagram below? This is a UART. This has odd parity. There's 1 stop bit and 1 start bit. So we can ignore this guy and we ignore this guy. So we're just looking at the ones between, right? So I'm only seeing 1 bit in between those two. And so if he had his odd parity, then and there's 1 bit, that's how many 1 bits there ought to be. So that blank one should be a 0, right? Yep, 0. And for an SPI channel with CPOL 0, CPOL 1, when does the data signal change? Okay, so if CPOL is 1, the data signal is going to change, or CFA is 0, the data signal is going to change before the first clock edge. Right? Because if CFA is 1, I have to read on the first clock edge, right? And so what is the first clock edge? Well, the first clock edge would be falling because CPOL is 1. This, it starts out 1 and falls, right? So it's gonna change on the falling edge of the clock. Yeah. Okay, any questions? Okay, I think the next quiz is the last one on the bus protocols. So last lecture, we started talking about FPGAs and SystemVerilog. I think all that material was a review of stuff you had in 3.13 and 6.11. In this class, as I mentioned, we want to try to combine those two things together. We want to be able to do platform design and hardware and have them communicate, okay? So in the first lab, which I've got posted there, this is lab 2, the second lab. This one asks you to design a Nios 2 based system on chip and develop associated software that will use pulse width modulation to modulate the intensity of this 26 LEDs. The LEDs on the board, on the FPGA board, right? So when I say modulate the intensity, I'm talking about dimming and brightening them as opposed to turning them on and off, which is what the board does when you power it up, right? The trick here, though, is there's a couple issues. The first issue is that if you go into Platform Designer, no mention of pulse width modulation. There's no IPs for that, which is really surprising to me. Because if you get an Arduino, even the lowest end Arduino, the Atmel 328P, it's got hardware PWM in it. So why in the world does Intel not understand that we need PWM? Unclear. So that's a problem. In Lab 2, we're going to solve that by using bit banging for Lab 2, and then we're going to develop a hardware PWM in Lab 3. The other problem is, I lost my train of thought. What's the second problem? I don't remember, but that's basically how we're going to solve it. We're going to write some software, and we're going to do bit-banged PWM. Okay, so I mentioned all the parts you needed last class. You need a clock source, which is it's kind of a dummy component. It essentially just adds it adds a input pin for the clock from outside the Nios system that comes in from lights.v. That's your top level design in Verilog. I don't know. That wasn't the reason I'm mystified by this. If you're wondering, is because in the older versions of the tools that wasn't there. It would just automatically add a clock pin for you. But they added this thing now where you add the clock source. Then there's the Nios 2F processor. There is an option for the Nios 2 Classic. I don't know what that is. I don't know how the Nios 2 Classic is different from the Nios 2F. So just use the Nios 2F. Then you need the PLL component. Now, by the way, this component, notice that it's specific to the DE2 series boards. If we weren't using this board, this would be a little bit more challenging. You'd have to, actually I'm not even sure how you'd solve this if you didn't have a DE2 board. You'd have to put in a phase lock loop component somehow to get the clocks you needed. But luckily, we have this really handy-dandy component you can put in, and it'll generate the clocks that are needed specifically for this board. And then we need a 26-bit parallel I/O. Now, the parallel I/O is kind of neat because this is essentially a bridge between the Avalon bus and the external world. So this PIO thing allows you to issue a store instruction or a load instruction and interact with pins. Right? So it's basically like, you can think of it as a bridge between the bus. When I say bus, I mean like the I/O, the programmed I/O thing, the Avalon, the load store instruction thing, the software, and just raw pins. And so we're going to add that 26 because there's 26 bits because there's 26 LEDs, and they should be configured as outputs because we're doing output mode, right? They can be inputs. Actually, you could do input output for those PIOs too. I've never done that. I don't know exactly how that would work. I mean, obviously you could load or store from them, but I'm not sure how you would wire that up. But in our case, we're just going to make them outputs. Then there's the second clock source. I talked about that last time for the SD-RAM. And then the performance counter, and I'll talk a little bit more about that. Did you guys use that in 313, the performance counter? Cycle counter? I used to use it when I taught 313. So that's needed because we need a clock. We need a time reference for the PWM. In fact, you're going to need a time reference for any kind of real-time computing or any type of control. Anytime you're doing cyber physical systems or control systems, you need a clock of some kind. Arduinos have this too. They have a cycle counter. In fact, the PWM and the cycle counter are actually part of the same hardware in an Arduino. And then JTAG UART. Okay, and then I have a little description of how to connect everything, and I'll go over that again today. Okay, so the objective here, and this is the part that's kind of confusing. So the problem is that with PWM, you have two different time scales that you have to worry about. You have a time scale that is the period of the PWM. So PWMs usually operate in the tens of kilohertz range, which is the microsecond, tens of microseconds. Tens to hundreds of microseconds, which is pretty short period of time even for a computer, right? That's why, by the way, PWM is typically not bit banged. So we want to do it in this lab just to have the experience of having done it. But even on Arduino, there's usually specialized hardware. Intel doesn't know this apparently, but there's specialized hardware for PWM because PWM is a very short time scale. You have to be able to toggle that PWM signal. The whole period may only be at 100 kilohertz. You only have 10 microseconds for your period, right? 10 microseconds. But then the duty cycle is a smaller portion of that 10 microseconds, right? So if your duty cycle is, say, 20%, you're now having to operate on a time scale that's 20% of 10 microseconds, right? So 2 microseconds. That makes sense? That's not a lot of time for the processor to get its game together, get its act together, right? So that's a fast signal. But then, whenever you have a signal that you're controlling with PWM, like say audio, like say you're playing audio, a Class D amplifier, by the way, like if you have Class D amplifiers are for PA systems and home audio, broadcast audio. Like if there were speakers in this room, it would probably use a Class D amplifier. Class D amplifiers are just driven by PWM. So instead of having an analog signal, you actually put a PWM signal out, but then you modulate that to create an audio signal, which itself is another analog signal that has dynamics, right? And that's on a different time scale, right? So in this lab, we're going to have a time scale called the dim period. The dim period is the period, the repeating period over which the lights on the board will go from full intensity down to zero intensity, so go from full brightness to off, and then back up to full intensity, right? And so that time scale is going to be about 2 seconds or so, right? Because we want to emulate this breathing effect where the lights kind of dim out and then brighten up and then dim out and brighten up. So your code, since you're bit banging this, you're writing code that controls this in software, you have to keep track of two time scales. The one time scale is controlling the PWM signal, which happens very fast, and the other time scale is controlling the dim period, which happens slow, right? Likewise, if you were controlling an audio signal with PWM, you would be sending a sound wave out, right? An audio signal, but modulating on a PWM signal, which is a much faster time scale, right? So the PWM constantly repeats, but over time, the duty cycle of that constantly repeating signal is being adjusted in order to implement the other thing that you're controlling on the larger time scale, right? That's what confuses everyone in this lab. That's the tricky part. So this plot is trying to show the objective here. So we have the duty cycle. So the axis of the duty cycle goes from 0 to 1, or 0 to 100%, right? And then we have the dim period. The dim period is a parameter. You can set this in your code to whatever you want it to be. So it could be 10 seconds, 2 seconds, 1 second, half a second, whatever. And you're going to start out with full brightness. And once you get to half the dim period, the light should be off. But it should happen linearly, right? Now, the problem is that there's not really a linear relationship between the duty cycle and the brightness coming out of the LED, right? I think by the time you get to 20%, the thing's off. Basically, it's not linear, but we don't care about that. We don't have any way of actually measuring the actual brightness coming out of the light. We don't have any way, like you could do that conceivably with some sort of, photo detector or light sensor. We don't have that. I thought it would be neat actually to do something like that, but I don't know how to do that. So we're just going to assume that the duty cycle corresponds to the brightness of the light. And so we want to basically bring it down linearly from 1 to 0 and then back up to 1, right? And then repeat forever. Okay, and we want to be able to change in your software the dim period, but also the PWM period as well, the PWM frequency. Now you might say, what's the point of that? Well, because I don't really know how fast the PWM signal needs to be to do this. Because if you make it too slow, you might see like flickering. You might be able to detect the switching of the lights on and on, right? Because the LEDs LEDs are on or off, right? But you're switching them on and off really fast, and you're changing the duration that they're on versus off, right? If that PWM frequency is too low, you'll start to see them flicker, right? In fact, I don't even really know if when it's fast and they don't appear to be flickering, if they are still flickering, but they're just flickering too fast for you to be able to perceive. Or if there's capacitance inside those LEDs to where if you toggle them fast enough, it actually does create an analog voltage inside the LED through the capacitor, through a sort of a low-pass filtering effect. I don't even know. I don't know what the answer is. I don't know how it works. It just works. If you make the PWM fast enough, it makes the lights appear to dim down and brighten up. Whether it's through an optical illusion of them flickering really fast and you don't notice it, or through some kind of capacitive low-pass filter effect inside the diode, unclear. But we want to be able to play with that, and change that. The problem, by the way, is if you have a hardware PWM, like on the Arduino, you usually can't change the PWM frequency. It's locked. It's like they'll say, yeah, it's 10, unless you have an expensive one. Like I think the Intel Galileo had programmable PWM. But a lot of times they'll just say, yeah, it's 25 kilohertz, you got to live with it. But we have the ability to change that, right? Now you might say, wait a second, but how does the software know the speed of the PWM, or how does it calibrate? What's the calibration? It's the cycle counter. It's that performance counter. So the software has the ability to see a 50 megahertz cycle counter, and it's going to base all of this off of that 50 megahertz. So basically what you're going to do is you're going to convert a 50 megahertz counter into a PWM signal and into this dimming effect as well, right? So it's really what you're doing is essentially a conversion process. You're going to be continuously reading the performance counter and then doing some calculations in order to convert that performance counter, basically by using a modulo operation, converting that into a PWM and this dimming pattern, the breathing effect, the off and on thing. Does that make sense? Okay, so I tried to explain all of that in the lab sheet. Hopefully, Oh, and I actually gave you quite a bit. Oh yeah, I give you quite a bit of the code actually too to do that. Yeah. Oh, one other thing too. Yeah, we noticed something over the past couple years. So the problem is that if the Neos processor is a 32-bit processor, and at 50 megahertz, if you have a 32-bit value and you increment it once every clock cycle at 50 megahertz, it'll roll over in 43 seconds. That's all it takes to, you think a 32-bit value, it's like, well, it goes up to 4.2 billion. Yeah, but 50 megahertz, it'll roll that odometer around in 43 seconds. And the problem there is that if you keep reading the 32-bit counter, eventually you're going to read it once before it rolls over and a second time after it rolls over, and it's going to screw up your code, right? So as a result, the performance counter needs to be read as a 64-bit value, which is such a large value that it would take, even the universe will be gone by the time that rolls over, right? It'll outlast the universe, the age of the universe. That's how, so you need to read it as a 64-bit value. Now, it used to be, in the old days, all you had to do is do little shifting operations. You could read the upper 32 bits, read the lower 32 bits. That takes 2 program I/O operations, and then you just shifted the upper one and ordered them together, and you were done, right? The problem is that at some point, and I don't know when, that stopped working. I think it was when we upgraded Quartus to 18. We used to use Quartus 16. We went to Quartus 18, and they changed the compiler. And GCC suddenly became incapable of doing that. Like there's a bug of some kind in GCC. It would not allow us to do it that way. So then we discovered that the only way to do it was use a union in C, right? Which probably makes more sense, but the code is a lot more complicated than just reading it twice, shift and OR, right? So you can use a union. I don't know, did you guys ever talk about unions in 240? This is a C, this is a classic C construct. So, when you're learning Java and C++, you might not have ever encountered this. So a union is like a structure or a class. The difference is that when you declare a class or a structure, everything that you declare in there is held in separate memory regions within that structure. Not necessarily one right after another, though. Sometimes they add a little bit of padding. So if I have a struct and I've got, like, say, 2 integers, that's a 4-byte value and a 4-byte value, then there'll be at least 8 bytes in that structure to accommodate both values. But sometimes there's actually more. You'd be surprised. Sometimes the compiler will put a little padding in between them. So you're like, I got 2 integers, but it's like 12 bytes. What's going on? There's actually an option that you can say packed an attribute. You can tell it to pack and use the minimal amount of space in C. A union, on the other hand, though, is overlapping all of the things that are declared in there. So if you have 2 integers, say you have a union and there's 2 members, A and B, and they're both integers, they will actually overlap in memory. So if you changed A, it will also change B because they're overlapping. Now you might say, what's the point of that? That's pointless. Well, it comes in handy whenever you have things in a union that are of different sizes. Okay, so if in the union I have a struct in the union that's 64 bits that is comprised of 2 32-bit values, right? And then in parallel to that, I have a 64-bit value called raw. Then I can read the high and low part in this structure. This structure, they're separate. So I could put value in high and low in this structure, and by doing that, I'm also filling in the 2 halves of this 64-bit value that sits in the union with it. You guys with me? And then all I have to do is when I can write it through 32 bits, but then when I read it, I can read it as the 64-bit value. That's the point of this, right? I need to be able to write it as 32 bits, 2 32-bit values, but when I use it, I have to use it as a 64-bit number. Does it make sense? So I write it through high and low, and I read it through raw, right? I don't know how else to do it because, like I said, we used to just have a raw value and just shift high by 32 bits and OR it with low, and we were done. But then, like I said, GCC lost the ability to do that. Okay, so the way you fill this in is you say oh, by the way, I don't know, the other thing about this that may look confusing is instead of declaring these types, I just declared the types and then used them immediately, right? So I say union, and then I define the union, and then I give it the name count. So it's the count, right? Likewise, the structure, I define the structure and also name it parts. So inside of the count, inside of this count value, I have two things. I have parts and raw. And inside parts, it's further broken down into high and low, right? So that way, if I say count.parts.high, I can then use the IO read intrinsic to pull in the upper 32 bits, right? And then counts.part.low, I use to bring in the lower 32 bits, both of which through this IO read thing, right? And IO read, remember, is just a load instruction, but it's a load IO instruction. So that's why I didn't use an indirection, a dereference here, a star. I used the intrinsic because you have to bypass the cache. I don't want to pull this in from the cache. I want to pull it in from the hardware, from the counter, right? So, and then the performance counter 0 base is the base address of the performance counter. And then this 0 and 1 is the offsets. Now you might say, wait a second, I thought you said they're 32 bits. So how can the offset be 1 byte? That makes no sense. Makes no sense. It should be 4 bytes. This is in terms of words, because it's dumb. I don't know why they do it that way, but for whatever reason they use a word offset instead of a byte offset, as if we're not smart enough to figure out bytes and words aren't the same thing. So it's 0 and 1 instead of 0 and 4. Now you might say, well, wait, how did you know what the offsets are supposed to be? That's in the documentation for the performance counter unit that we added in the hardware. It's documented. There's a register map in there. In fact, I think I give you the, hopefully I have it here. Let me see, make sure I have it here. I think I have it. No, I don't. But it's in the documentation. So if you go inside of the platform designer and hit the help button on the performance counter unit, it'll show you. Okay, everyone with me so far? Does that make sense? Okay, so in the past there was a lot of confusion about how to compute these values. So a lot of the calculations are in the lab sheet. I put them in to make it easier for you. We do need to have a thing at the top of the code. Yeah, so we want a thing at the top of the code here of 2 variables. These could be global variables. And we want to be able to set the PWM frequency and the dim period. So in this case, the frequency is 10 kilohertz, 10 e to the third power, 10 times 10 to the third power, 10 e3, right? And then the dim period is 2 seconds. So this is in hertz and this is in seconds. That's a little weird, right? Why typically you use period or frequency. We're mixing them here, right? So just be aware of that. With PWM, usually PWM is expressed in terms of frequency, but the period, this is how long it should take the board to dim out and light back up again. Okay, does it make sense? You guys with me? So we want to be able to change this, recompile your code, rerun it, and we should see the impact of those changes. So if I change this to 4 seconds, recompile and re-download on the board, I should see the dimming and the brightening up taking 4 seconds instead of 2. Right? And then I can take this frequency and I should be able to crank this down to 1 kilohertz, right, or 500 hertz, and I should start to see some crazy artifacting with the flickering or whatever. We get to see what happens when you use a very low PWM frequency. Not sure what to predict there. I'm not sure what to expect, I should say, from that. Any questions about that? Okay. Let's see. Anything else? Oh, here we go. Yeah, sorry. The performance counter. So, by the way, the performance counter has this weird thing where it has registers that if you read them, one thing happens, and if you write them, something else happens. Right? Sometimes you'll get that with I/O registers, with programmed I/O. So when you read register 0, and when I say register 0, I mean you set the offset to 0 in the I/O read. You get the lower 32 bits. Get the lower 32 bits of the counter. Okay? But when you write register 0, you don't write the lower 32 bits of the counter. That would be too obvious, right? Instead, that's what stops the counter. That's the signal to tell it to stop counting. And it depends what you write. If you write 0, it resets it. I'm sorry, when you write 0, it stops it, and when you write 1, it resets it. So it even depends on what you write, the value that you write to it. And then when you read register 1, it's the upper 32 bits. I should say bits, not butts. And when written, register 1 starts the counter assuming you write 0. If you don't write 0 to register 1, I don't know what happens. Unclear. It may have an unpredictable result. Make sense? So basically you just do that through the IOWR and IORD functions. And again, I don't know if you use those in 313. In 313, in the old days, we used to rely on those functions a lot, just the low-level I/O writes, I/O reads. And then over time, we started adopting more of the BSP helper functions. Like for example, the frame buffer for VGA. We used to write into the frame buffer with I/O write, I/O read, but over time we just had everyone just use the little helper, the little pixel write functions that they provide in there. It's a very thin kind of interface, thin driver. So I don't know if you guys are still using I/O write and I/O read for anything. The performance counter also has little helper functions too, but I don't find them to be very helpful. I think this is much easier. Yeah, they even have like a function where you can pretty print the counter value. Like there's a function you can call and it'll print like a little table to the console, but usually when you do that it just prints out garbage. So I don't know why. It's a little unreliable. Okay, any questions about this? Okay, so let's just wanted to quickly go through. I've got the design pulled up that I worked on last time. If we bring up the platform designer, I just wanted to show you the performance counter because I hadn't added that. Oh, that's not good. Do I have to open? Up. Lights.qsys. There we go. Okay, so do I not have the right? Oh, I have the wrong. Oh, sorry. That's my fault. I had the wrong project open in Quartus. That's why it didn't open that automatically. That's no problem though. Okay, so here's the platform design that I have built. And so the only thing, I think everything in here, I got everything I need. The only thing I need to add is the parallel I/O and the performance counter. So the performance counter is performance counter, it says performance counter unit for Intel FPGA. This thing right here, I don't know if you probably can't read that in the back, but it says performance counter unit for Intel FPGA IP. So you double click that. And you don't actually have to change any of the settings in there. It asks you how many simultaneously measured sections you want. It doesn't matter. We're only using one. So you can just use the default value, just hit finish. And then you have to connect the clock. Now this is pretty important here because essentially this is just a counter for the clock cycles, right? So you got to make sure you use the right clock. So we have 4 options for the clock. Why do we have 4 options? Well, there's one clock is the raw crystal clock from the board, right? That's the dirty clock. There's a clock, another clock called sys clock, which is the system clock that's supposed to run most of the things. Then there's the SDRAM clock that runs just the SDRAM, right? But that's only 3. What's the 4th one? Oh, the 4th one's probably that. What is the 4th one? Clock 1. Oh, that's from, I guess that's another miscellaneous clock that we don't use for anything. Okay, so I'm just going to use sys clock, right? You guys see that? So that's the system clock, and you can see that it's the same one that's connected to the UART, which is good. We want that. And then there's a reset. We want to use the same reset everyone else uses. And we have a slave port. We have 2 options for the slave port connection. That can be the instruction master or the data master. You got to use the data master for this, because otherwise the IO read, IO write functions won't work on it. And then it says we have an overlap. The control slave overlaps the JTAG UART. So this is saying that the performance counter has the same IO address as the JTAG UART. So how do you fix that? You just go to, I think, System, Assign Base Addresses. Yeah, and it fixes that. Right? And the other thing is the parallel IO. You guys use this, I think, in 3.13. Width is 26 bits. It's an output. This thing is kind of cool, this individual, I've never used this, individual bit setting. I don't know exactly how that changes the interface, the program interface. I've never tried it. But in this lab, we want you to just control all of the LEDs should be, all 26 LEDs are going to be brightening and dimming at the same time. They're all going to be operating in lockstep, right? In the next lab, lab 3, we will have them individually controlled. But in this lab, they're all tied together, all shorted together. So I'll just hit output, OK, and then again we want the clock is the system clock. Wrong. Wait, where's clock? Where's the clock? Sys clock, is that right? Sys clock, reset, data master. Nope, data master. And then you have to then, don't forget, with the PIO you have to expose a new output. Like you have to create a new pin, so you gotta do this export thing. Double click to export. We want to export this signal, which I'm just going to call it LEDs. Is that good? Should be fine. Yeah, external connection LEDs. You guys see that? So this is then going to require you to change the lights.v, the wrapper, right? So you guys have done this before in 3.13, and there are instructions in the lab sheet too, in case you forgot exactly how to do that. Okay, so that's it. That's all you need. And then the instructions for the software part. Well, you know what? Let me show you that. It's not going to take me long. I think it'll be worth it. Okay, so for the software, you'll notice here that in this directory, oh, that's weird. Okay, usually you have I must have never generated that. Hold on, let me save this. Oh, no, save this. Okay. Yeah, I guess I didn't generate it. When I exit here, I'm going to reopen my, oh, no, don't generate it. No, just exit. Actually, you know what? I don't think I might not need to exit. Let me try generating it. Okay, so once I do that, I should be able to see, nope. Where are you generating it, sir? Interesting. That's suspicious. Okay, well normally you would have normally in your project directory, you would have a subdirectory called neosystem in here, right? Which is where all the generated files are supposed to be going. I think the problem is that when I initially opened this, I opened the wrong project. So let me fix that. Let me go, I'm going to exit out of here. And I'm going to go into Quartus, and I'm going to close this project because it was the wrong one. And I'm going to say, I'm going to open Lights, open project. I'm going to go up, go to Lights. Oh, okay, I really screwed this up. I don't even have the Lights project file in there apparently. Lights. Yeah, there's no QPF file. Okay. Okay. Well, anyway, not a big deal. I think I screwed up when I created that project. But okay, so I'm in the Lights directory though. So, and I do have the SOPC info file. So if we take a look at that, so you can see this is an XML file that basically just contains everything that you put into the Platform Designer, right? And so that is what you're going to need to create the software part of this. Now normally you guys do this in Eclipse, and you can still use Eclipse if you want. I don't like it. It's just way too unreliable. Instead, I've been using the command line version of the tools. Do I not have the right, yeah, I don't have the right PowerPoint. Lecture 1, FPGA design. All right, so if you go in the slides, and I think I have this in the lab sheet as well. There are the commands in here to set this up. So the command is this. Neos 2, I'm going to copy this. Copy, and let's paste. Okay. So the command is Neos 2 software example create, and then you've got all these options. Now you'll notice that the SOPC info is specified there, right? Which is the one I've got here. Now in here I have Neos system SOPC info. Over here I've got Lights. I guess when I saved it in Platform Designer, I saved it as Lights as opposed to Neos system. It just depends on what file name you save that to. And then I get, and then it should generate that. Now in this case it's saying Neos 2 SW example create not found because I probably don't have my path set up right, but that's just because I'm on my laptop. It works on the lab machines. So that would be opt Intel FPGA 18.1 Neos 2 EDS, and then bin, right, and then software. Do we have it in here? We have all the commands in here. We've got configure soft and so forth, but we don't have the one I'm looking for, so I'm going to have to do the old brute force. So find -iname, and the command again is Neos 2 software example create. So Neos 2 software example create. Okay, there it is. So it's in opt Intel FPGA 18.1 Neos SDK2 bin. No wonder I didn't find it. Neos 2 software example create. Okay, and then you got to put the flags. I used to have these memorized. In fact, I'll just say, I'm just going to copy this part. Copy that, and we'll paste it. Okay, now it's going to say we have to change this SOPC info file to lights.sopc info. And now I get SOPC kit Neos 2 environment variable not set, so let's set that. So the kit Neos 2 equals, and this would be opt Intel FPGA and this would be SOPC kit. So what are we setting this to? Neos 2 EDS, I guess? I'm assuming. Export U. All right. There we go. Cool. There we go. Yeah, sorry, you don't have to set that environment variable because, again, we have this, or you shouldn't have to. If you do, let me know. But those environment variables should be set up on the lab machines. Okay, so it says generating lights BSP and lights create this app. So there's two directories, lights BSP and lights. These are the same two projects that you guys would have remembered from Eclipse, right? Remember in Eclipse, these two projects were there. Now they're just, they're in the directory structure. So I go to lights and let's see, what do we got? Lights and lights BSP right here. And then in lights, you do create this app. Oh. Neos, I got another path issue. Dang it. All right, hold on. Export path equals opt Intel FPGA. FPGA 1801, and then that would be a Neos 2 bin, and I'm guessing Neos 2 BSP. No? All right. SDK2, Neos 2 bin, Neos 2 BSP. Yep, there it is. Okay, got it. Sorry. All right, export path equals this semicolon dollar path. All right, here we go. And another thing. Oh, it's not finding it though. Oh, sorry. Sorry, screwed that up. My bad. There we go. And, all right, now it's saying it's not finding settings BSP. That was because I screwed up that directory structure initially. Anyway, it'll be fine on the lab machines. I just don't have my environment set up right. And I screwed up the creation of the project. But once you do that, you'll have both projects, and then there's a script you run, and it generates the files, and all of that is in the lab sheet. If you have any trouble, let us know. Okay. All right, well, that sounds good. I have a few minutes left. Let's continue on with the next lecture then. So I was also, last time I started talking about SystemVerilog. And this is just a review of the stuff we covered in 611. So the objective in Lab 3 is to use SystemVerilog to build our own PWM hardware that will allow us to control the PWM signal from software, right, without having to worry about bit banging. And so I'm going to just quickly review this stuff so we'll be ready for Lab 3. Okay, so I think I got through this last time, right? So you guys all remember how to build a module. So modules are, the module line has the inputs and outputs. We're using this logic type. And you don't actually have to, say input logic A, you can just say input A, but I usually just include it because you do need it for the outputs. So this is a little bit more verbose than it needs to be, but yeah, so I've got my inputs here and inputs and outputs listed. There's a semicolon there on the module line. There's no semicolon on the end module line, and then the stuff in between is the implementation. Generally, you'll have one module per file. And so then you can have things like behavioral Verilog where there's two ways to define behavioral Verilog. There's the assign statement and the always statement. And then structural Verilog is when you just instantiate modules and connect them together. Okay. Okay, and then you can also mix and match. You can have a mixture of an assign statement and instantiated components in there. Right. Okay, and then one thing that's often confusing for students is how the same signal has different names at different levels of the hierarchy. So this N1 signal that's defined in NAND is actually the same signal as the Y inside of the AND gate here, and it's the same as the A inside the inverter here, right? But this Y is not the same as that Y, right? Right? But that Y is the same as that Y, because they're connected, right? So this depends on how you connect the wires, right? Okay, so then we use a model sim to debug this stuff. Waveform editor, discrete event simulator. But here's the problem though. In this class, you really can't use that. Not if you want to test the interaction between the Neos processor and your hardware, because we don't have a way to simulate the Neos processor. Now, you can put in a test bench that pretends to be the Neos processor, right? So you could create a test bench that generates Avalon transactions. So the peripherals in this class are going to be Avalon slaves. Well, they could be Avalon masters too if you want, but we're going to be designing a slave because we're designing a peripheral for the CPU, right? So to test that, we would need some master to come in and do an Avalon transaction, right? Well, who's going to do that? Well, it's either a test bench or it's just going to be the Neos processor. But if you want to use the Neos processor, you can't simulate. You have to run it on the board. The only way to test this is not through the simulator then, is going to be through JTAG. It's going to be through signal tap. Does it make sense? You guys with me on this? So we talked about JTAG is used for testing chips. Signal tap is a program that's part of Neos. It's a tool that operates over top of JTAG, and it allows you to create a virtual logic analyzer. What's a logic analyzer? It's the digital version of an oscilloscope. These oscilloscopes have logic analyzers built in. So they have 4 analog channels that basically act like an oscilloscope. And then they have 2 16-bit like ribbon cables that you can plug in to connect the digital signals, and that's the logic analyzer feature, right? We still call these oscilloscopes, but technically they're oscilloscope and logic analyzer. Does it make sense? So logic analyzer is binary, 0, 1. Oscilloscope is you're measuring voltages, analog voltages. Okay. So what's a virtual logic analyzer? Well, that's where you put probes. Instead of connecting wires like you would the physical, like with these guys, you have to connect wires. You have to connect a lot of wires. In fact, it kind of sucks because, in fact, these are the wires. You have to connect all of these little tentacles to stuff. That's no fun. But signal tap, and this is actually just one. You can then connect 2 of these guys. So this is 8 bits and 8 bits for a total of 16, and then these things support 2 of these to get up to 32. I think you can put 2 of these in. But this one's 16. In signal tap, you don't have to worry about this. All you do is you go into the signal tap tool and you just create a table of signals you want to monitor in the FPGA in your Verilog design, right? That's all you got to do. And then the tool will put in a memory that allows you to store samples of those signals in a table, 1 per cycle. So you have to give it a clock cycle, a clock, and you have to give it a memory size, which could be, the default is 256, but you can bring it up to like 8K if you want to, or 16K. And that's the number of samples it will record whenever a triggering event happens, and then those get offloaded over JTAG, which then operates subsequently over USB, and goes into your workstation, and then you can look at a view like this, but not of a simulation results, but the actual signals as measured on the FPGA. It's not real time, of course, because you have to record the data and then offload it over USB. And USB isn't fast enough to measure signals at 50 megahertz. Maybe it would be ideally. I guess maybe in principle it would be. But with all the overhead of JTAG and all the other stuff that has to happen, I think in practice it's not possible. You can't do real-time data collection at 50 megahertz, and certainly not if you had 200 or 200 megahertz or 400 megahertz, right? You guys with me? So I'll show you how to use signal tap next lecture. But it's pretty simple. You just set it up and then you can monitor things. The problem is every time you want to add probes, you have to recompile your design and reprogram the FPGA. You can't add them after the fact. They have to be burned into the design, so to speak, because they're actually they're memory components that you're adding. Any questions about that? Okay, so that's simulation, and then or lack of simulation, rather, and then I think I briefly mentioned the always statement. Do you guys remember how to build an always statement? So an always statement is used for a combinational logic that has if, then, else's and case statements and stuff like that. Complex combinational logic. Combinational logic meaning that the outputs are updated as soon as the inputs change, or the outputs are a function of the inputs rather, and they update whenever the inputs change. And then you can also build it with sequential logic that has memory, right? So the difference there is the sensitivity list. If your always statement has a star or no sensitivity list, like in this case I have always at A, B, and C. A, B, and C are all the inputs. You can also just say always at star here, or you can say always underscore comb, right? All of those create combinational logic. On the other hand, if you have a clock in here, if you have a pause edge clock in the sensitivity list and you don't have like inputs like A, B, and C in the sensitivity list, then it creates memory, because then it basically the whole always statement triggers just when the clock event happens, right? So any inputs that change outside of the clock are just ignored. So you end up with basically a flip-flop type behavior, right? Where inputs could change but nothing happens until you get that clock edge, and then the inputs are sampled by the always statement and the outputs update. Okay? You guys remember that? Yeah, you getting some confused looks. Maybe you don't remember it that well from 611. But that's so in this class we have to use an always that's clocked in order to implement the endpoint on the Avalon bus. So the Avalon bus, and I haven't showed you that Avalon yet, but it's basically like SPI, where you go through stages. SPI has stages. There's the slave select, and then there's the address phase, and there's the data phase, and then you have to count 8 cycles, right? In hardware, all of that would have to be performed by a clocked always statement that would keep track of what's going on the bus in each clock cycle, because the bus protocol is a sequential process, right? You have different things going on at different times whenever you do a bus transaction, and so you need to use an always statement for that. So it's important that that you guys be comfortable with that. Okay, so I'll show some. I got a few more examples here. Okay, so this is a bunch of examples of always statements that are clocked. Each one of these is just creating a flip-flop, though. Some of them have enables, some of them have resets, some of them have asynchronous resets, some have synchronous resets. This one's actually a counter, not just a flip-flop. It counts, so there's no input. It just counts every cycle, and there's no way to disable it or reset it because I just don't have that functionality defined in there. And then you can do something like this, which is a counter that has control signals on it. So this one has a reset for resetting the counter. And it also has an up and a down. I can count up or I can count down. Or if I have reset is not asserted and enable up is not asserted and enable down is not asserted, then it just holds its old count, right? So this is basically similar to the performance counter that we're adding in the Neo system, except that one just counts up. It doesn't have a count down feature. So when we build the PWM logic in hardware, you're going to have to take the kind of the code that you wrote in Lab 2 and essentially convert it into Verilog, right? And part of that is going to be implementing your own counter, because you don't want to have to rely on the performance counter when you do your hardware PWM. Does that make sense? Okay. So this stuff is just all... Oh, and one other thing too I want to mention, this is something that you may not remember. In always statements, there's 2 types of ways to assign signals. There's the blocking and non-blocking, right? Blocking is less than equal and... I'm sorry, non-blocking is less than equal, blocking is equal, right? Whenever you do an assign statement, you always just use equals, right? Because that's a totally different construct. In an always statement, whenever you assign an output, you can choose between this blocking and non-blocking assignment type. The convention is to always use the blocking type for combinational logic, in other words, if it's not clocked, and use the non-blocking for sequential logic. And usually if you follow that convention, it's fine. The real difference is that if you use a non-blocking, whenever you assign something, that assignment does not take effect until after the always finishes, and after all the signals have been established for whatever triggered that always, right? And the reason I say that is because this has implications not just within an always, but across multiple always blocks. That's where it gets really confusing, right? So what I mean by that is I set N1 here, and then I read N1 in the next line of code. This N1 on the next line of code is not going to be the updated N1. It's going to be whatever it was, right? And then N1 will get updated, but not until everything's been settled, right? Not until the end of that cycle, right? Which means that these two lines of code, the order of these lines of code don't matter, right? I can swap these two lines of code, and even though there appears to be a data dependency between them, because I write a value that I then read in the next line of code, that data dependency doesn't really exist because these are concurrent. These have concurrent semantics. So these are basically creating two flip-flops that are connected in series. So I've got a 1 cycle delay between D and N1, and a 1 cycle delay between N1 and Q, and that's going to create a 2 cycle delay between D and Q, right? So this creates a shift register. Over here, if I use just the equal sign, then what it's going to do is it's going to essentially take this value, N1, and it's going to substitute D into where I had N1 in the line below. So this will this is redundant, because this will just end up creating one flip-flop. You guys with me? Now you might say, why is this relevant? Oh, it is. This will be relevant when you design your hardware. You have to be careful, use the right kind of assignment statement when you design your Avalon endpoint. But I'll talk more about that once we get closer to Lab 3. I'm getting ahead of myself a little bit here. Okay, and one other thing you're going to need too. There's this thing called the generate statement. We didn't cover this in 6.11 because it wasn't needed in 6.11. So the generate statement is a for loop, but it's not a for loop like you think of a for loop. It's a for loop that's used for stamping out multiple copies of something, of a module, of anything actually. It doesn't even have to be a module. So if you have a snippet of code, usually it's a module instance, right? But not always. It doesn't have to be. It could be assign statements, right? Let's say you have an assign statement, and you want to have 10 of them, right? You can use a generate statement for that to generate 10 assign statements, to create an array of assign statements. Now, what could we possibly use that for in this class? Can you think of a reason for this? You know, Sai? Well, we've got 26 LEDs on the board, right? So if we wanted to generate logic in order to control those 26 LEDs independently, we would use an assign statement to generate a pulse width modulator for all 26 LEDs, right? As opposed to just copying and pasting, which you can also do. You can copy and paste the code too, but it's a lot more convenient to use this generate statement, right? Same thing goes for the hex displays. There's 8 hex displays on this board. If you wanted to put hex decoders, you could generate 8 hex decoders, right? So you could write one hex decoder, but then just copy it, let the compiler copy and paste it 8 times. Now you might say, well, yeah, but like, what's the use of that? You have to, obviously, there have to be some difference between the instances. Yeah, the way that works is through the index variable I. So I'm generating this with I equals 0, I less than n. And if you look at the code, in this case, I'm generating smaller adders to create a bigger adder. I'm creating I'm creating a bunch of adders that are connected with the carries, carry out, carry in to each adder, right? But you'll notice that the I variable is what's used as part of the expression that determines the bit ranges that are being passed into the adder. You see that? You see it says 8 times I plus 7 down to 8 times I. So I is being used to determine which chunks of bits I'm sending into each adder. You guys with me on that? So in lab 3, you're going to have one PWM counter for each, actually say one PWM duty cycle for each LED. So you can take all of those duty cycles and put them into a big array of bits. And then when you write your generate statement, the I value will allow you to choose which bits you're assigning to each LED, right? That's the idea with the generate statement. The syntax is so messed up, though, that I have to, I've been writing these for 25 years, but I still have to go back every time I write one of these and check the syntax, because the syntax is totally bonkers. So you have to say genvar I. I don't know why not just integer I or something? Why genvar? Genvar I. Then you have to say generate 4, and then after the end of that, after that last parenthesis, you have to say begin. Okay, I'm okay with that. But then colon. And then you give it a gen name. The gen name is the prefix that's going to be appended to each one of these adders. Notice that the adder is the name of a module. I don't have a name for the adder. Normally you have to give a name. When you instance a module, you give it a name. The name of the modules will be gen name, but then it's going to append I to it. Oh no, I'm sorry, there is a name actually here. Sorry, my adder. It says my adder. I guess it adds the, I forget how it works. Like actually, it uses these things to generate the names, because obviously they can't all be called my adder because I'm generating a series, right? But you say colon gen name, and then end and generate. Why, I don't know why you need both end and generate, but then everything in between that is what's going to be stamped out. So in this case, I have an adder, but you can actually put you could put an always statement in there if you wanted to, and it would just create multiple copies of that always statement. Or you could put assign statements, or you could put multiple instantiations of modules. Whatever you want to put in between inside that generate statement will get essentially copied and pasted, where the only differences are the names assigned and the bits that you connect to those things. And also this, I don't know if I covered this yet, the hashtag here thing, hash sign, these are parameters. So this allows you to set individualized options for each of the adders. In this case, it's the bit width, 8-bit. So I'm creating multiple 8-bit adders to build a bigger adder. If you guys remember from 611, remember when I covered prefix adders and carry look-ahead adders? And they were like weird, like array structures where you build up a more complex structure from interconnecting smaller ones. That's the sort of thing you can do with a generate statement too, right? Okay, sorry, any questions? Okay, we'll be, Thursday will be a lab day, so you can work on lab 2. The due date, I gave you till October 6th to finish that, which I think is like 3 lab periods in here. So I think that's probably more than enough, because it's a fairly simple lab. We have had some issues though with that lab that I haven't fully worked out. Last semester, there were a couple groups that did the lab too, and they were getting some strange flickering on the LEDs. We never quite worked it out. So I didn't penalize them for it because I couldn't figure it out myself, but hopefully that doesn't happen again. But sometimes weird stuff like that happens with this. This lab is a little, bit banging PWM is kind of a risky, sort of unreliable thing. So hopefully we can make it work out. Okay, thank you.